you, Harald.
So thank you very much, Anurag. It's a pleasure to be here today and tell you a little bit what we're doing. So I followed your instructions and have a significant part on the facility itself, who we are, how we work, where we come from, what's the future. And then a lot of information also for students or potential users that we may have and have never been at the facility and would like to learn a little bit about what we are doing. So let me get right into it. So the ESRF is an international facility, is a facility that was actually in the making for a very long time. It exists now for more than 30 years and has a 30-year-long history of success and excellence. Now, the whole thing started in the 70s, actually early to mid 70s, when scientists in Europe started to discuss the possibility of having a large international facility in such a way that it would actually encompass more than a single country could achieve in Europe. So we had something like 12 member states ganging up in the beginning who signed in 1988 a convention to create the ESRF. And that was the first international synchrotron radiation facility. Before that, all the facilities were national facilities and today still are, apart from one other international facility that came up recently, which is Sesame in the Middle East, and on the X-ray laser side, the European XFEL, which was built on the model of the ESRF. So in 1988, these 12 member countries signed a convention for the construction of the ESRF. And believe it or not, this is something that you wouldn't see these days. It was built in 4 years, the whole facility. In 1992, we had the first electron beam in the storage ring. And I myself did my first experiment in 1993 here at the ESRF, 1 year before it officially started, on a beamline where it was a brand new beamline. I was the very, very first person from outside on this beamline. In 1994 was the official inauguration with 15 beamlines built out and operational. The whole facility was built in time and within budget. And in 1998, the facility reached its current steady state, which is about 40 beamlines plus minus. Today, we are more like 45, 46. Where everything was delivered in time and within budget. So then we were operating for a while. And in 2009, and you may have noticed the coincidence, I came in 2009, the upgrade program phase 1 started. That was a program that was discussed for a few years with our governing bodies, in particular the Science Advisory Committee and the Council, which is the topmost decision-making body and also provides the funding. So they decided that after something like 20, 25 years of operation, it's time to think about the next phase for the ESRF, since, as you can imagine, the technical infrastructure ages. And in the meantime, there were also something like more than 20 other third-generation facilities built. The ESRF was the first third-generation facility, and what that means I'll show a little bit later. So then we embarked on this upgrade program, which was the first part was 7 years. And this was done successfully in time and within budget. And one of the charges there was to think about a new way of accelerating electrons with a higher to deliver X-ray beams with a higher brilliance, a big step in the delivery of source performance. So the idea for this here in the facility was then worked out in 2012, put into a book that we call the Orange Book that you see down here. The history of the ESRF is in booklets. So you can see this, the 4 books before the ESRF was even conceived. You see the blue book, the green book, the black book, the red book. There was a white book as far as I know, and also a yellow book, which we can't get hold of it anymore. So we don't have a copy. Otherwise, I could show you the first page, but I don't have one. And then the upgrade programs, which are sort of 10-year plans for the facility. So then in 2015, our council launched the upgrade program phase 2, which we call EBS, Extremely Brilliant Source. And this is what we have been doing since then. We've actually designed, manufactured, assembled, installed, and commissioned that source. And since summer last year, we're back in user service mode with this new source. And I'll show you a little bit later on what that means. So this is what the ESRF are. We have 21 partner countries, of which 13 are member states with their corresponding share, which is noted here on the left-hand side, and 9 countries which are scientific associates, which have the same right of use but no voting rights. So as I mentioned before, the ESRF was the first 3rd generation synchrotron radiation source, and we're now the first 4th generation high energy synchrotron radiation source in the world. And again, I'll put that into context a little bit later. So the ESRF is in Grenoble in France, and this is not a standalone institute that is just isolated here somewhere. We have here a very nice campus, which is called the European Photon and Neutron Science Campus, EPN campus. And there are 4 institutions on this campus. 3 of them are international institutions. There is the ILL, which is the oldest one on site. That's still the most powerful neutron source, continuous neutron source in the world, where the neutrons are supplied by a reactor, which you can see here under this big dome here. Then the EMBL, the European Molecular, an outstation of the European Molecular Biology Laboratory, and the ESRF, which was the 3rd facility to appear here. And more recently, a French institute, which is the French National Institute for Structural Biology, which is actually housed in this building here. So you have the ESRF, the EMBL, the ILL, and the IBS here in this international campus. And this entire ensemble, this international campus, which is actually in this part of this semi-island, is embedded in a larger, let's say, research campus here, which also includes the Grenoble universities and the big research organizations in France, the CNRS and the CEA. You see here the university, the logos of the university here, and it even encompasses a relatively well-known management school here with which we also collaborate. So this is a very nice, if you want, innovation campus that we have here, which is called Giant. There are also quite a few companies here, which brings together research, innovation, and higher education in one location. Just to give you a frame, we have about 10,000 students here, 10,000 researchers, and more recently, the local authorities have also started to develop housing. They would like to develop housing for 10,000 people here as well. So this is starting to become a quite lively and modern part of the city, which you can see here at the confluence of these 2 rivers. There's the Esre on the left upper side and the Drac on the lower right side. And in between, you have this big campus here, which has all these research institutions in there, which is quite a unique setting here. So what do we do? Well, we provide X-rays. We are a user facility, which means we have no research charge per se at the ESRF. We're not, for instance, a battery research institute or a catalysis research institute or environmental research institute, but we supply tools to do all this research. And if you would map this today on, for instance, the UN Sustainability, Sustainable Development Goals or the Horizon Europe program for research and innovation, you will find many of the topics that are in these development goals or the research and innovation goals you find at the ESRF. And just to name a few, very prominent one is health and health innovation. We do a lot of research in infectious diseases, on viruses, and many other diseases. We do a lot of material science. This is what hard X-rays or high energy X-rays are particularly useful for. We have many users who work in the energy sector for clean energy transition, energy storage, clean hydrogen production, stuff like that. Then a large section of the research at the ESRF deals with terrestrial and extraterrestrial problems. all the environmental stuff goes into that as well, as you can see here under point number 5, environmental and climatic challenges, water supplies, earth atmosphere, bio-based economy, and food security. So there's a lot of things that we're doing here. We serve a very, very wide community. So this is reflected in the scientific fields that are represented here. You find physics, chemistry, biology, and many other fields, which are all related to real-world applications, as you can see here. So chemistry, for instance, for the entire petrochemical industry, the catalysis that goes with it, soft condensed matter that quite often ends up in consumer products. That's all the plastics that we're using, or stuff that goes into the products themselves. Structural biology, which is very much related to health. Advanced materials, you can see here graphene nanotubes, or research into semiconductors, metals. In metallurgy, you see here extreme conditions that we are particularly good at dealing with, because we can provide very high energy beams, very small ones that can actually go deep into sample environments that can create those conditions. And then, of course, more and more important, applications in energy environment. Just to give you a feeling for this one, about 10 to 20% of the research we do today is in energy alone. And then, of course, there are the things that you see very often appearing in the news and in the media is cultural heritage. When we study priceless fossils, for instance, the earliest human ancestors here. This is one is a skull that is 2 million years old and has been scanned at the ESRF with a lot of results coming out from that, or the preservation of priceless arts and artifacts from the past. So these are all connected to fundamental physical, chemical, and biological processes that we're starting here. And as you can see from all those pictures, this is related, of course, directly to a lot of industrial applications. So we have a very large number of companies coming here doing their research here. And they do this partially in collaboration with academics, or in some cases, they come and pay directly to get access to the facilities here and develop either their science or their products. A large part of the industrial research is, in fact, published, even sometimes in very high impact scientific journals. So we're also very active in on the educational sector, and I just start here at the bottom, where you can see that under normal conditions today it's a little bit more difficult because we can't go out, but under normal conditions we have a program where we immerse kids in school into science. We call this Synchrotron at School, with about now, before the closure, we had about almost 1,000 participants per year. So we're really going out, reaching out to kids before they actually go to university to help them make a decision to go into science instead of doing something else like banking. This then goes on in the next higher level. For instance, if you go to the undergraduate level, the ESRF and the ILL offer together an international summer student program where we accept 20 students for 1 month with real projects. This whole program is funded by the ESRF and the ILL jointly, so we pay all the associated costs. So the students just come, enjoy the month, and get immersed in research. We do the same thing also for people who go for a more classical education, for handy jobs like sandwich courses, where you have two-year courses alternating at the ESRF and in school, which is also funded by the ESRF. We have a trainee program where students, this could be, for instance, students in the last year in their bachelor program or in their master program, come for up to 6 months to the ESRF, and this could be in engineering or in science. It's fully funded by the ESRF, and they stay here for 6 months, do the work for their thesis, submit at their home universities, and get their degrees. Then it goes all the way up to the PhD level. We have a PhD program at the ESRF that funds something like 30 positions normally, full positions normally. At the moment, it's more like 45 because we got some funding from the EU in a co-fund program together with the ILL again, so that we have today 45 positions here. Many of them are co-funded. So in the end, we have a lot more than these 45 students here. And then at the highest level, since more than 25 years, we organized the Hercules courses in X-ray and neutron science, which is a course series with a lot of lectures, but also hands-on work on the beamlines where scientists from the PhD to the postdoc level can actually learn about the possibilities that we have at these facilities, and then eventually become users. So you can see that we're quite active on the education side as well. So what is the ESRF? The ESRF is an accelerator complex that actually accelerates electrons to 6 GeV, which is a relatively high energy for a synchrotron radiation source. So you have a LINAC, which is actually here in this little extension here on this building, where the electrons are then shot into transferred into a booster synchrotron, where they are actually accelerated all the way up to 6 GeV before they are injected into the main storage ring, which is this one here. So this is actually not a synchrotron, it's a storage ring, where the electrons are kept at a constant energy of about 6 GeV. And where, due to the bending they experience around this storage ring, they emit light. We also have specific sections in there, which are so-called straight sections, where we put insertion devices in there which produce an even higher level of radiation. We have a lot of instruments on this in this structure. At the time, it's more like 45, 46 instruments. There's always some on the reconstruction. 32.5 we operate at the ESRF itself, and 13 are actually operated by teams from our member states, which are nevertheless open for applications by scientists from around the world. We apply all the classical X-ray techniques, which are X-ray imaging, diffraction, scattering, and spectroscopy, and combinations between those, with beams that range all the way from 10 nanometers, this is the smallest beam size that we can produce, all the way up to centimeters. And in 1 year from now, the largest beam that we will have will be 40 centimeters in size. So you can see this spans many orders of magnitude, not only in size, but also in energy. We go all the way from let's say infrared or soft X-rays, all the way up to almost gamma X-rays, gamma rays. So this is a large operation. We have 10 panels that look through something like 12 panels that go through something like 2,500 scientific proposals per year. We accept about 1,000, which lead to about 2,000 experimental sessions. And this is only in the public program on the 32.5 beamlines. Then we have the 13 private beamlines. So that in total, we have about 10,000 users coming to the ESRF every year, doing close to 3,000 experimental sessions. And from this, we have around about 2,000 publications that are coming out here. So this is a quite substantial operation here. So this is the publication record that we have here that was at the very beginning of this year. In the meantime, 2020 is practically at the level where it was before, because there was more coming in. And if you look at publications with that appear in journals with a very high impact factor, you see that this one is going up nicely as well. We had last year, again, a record value because this was not finished yet at the beginning of the year when the statistics was prepared. So there's a lot of different science going on at the ESRF, and it's impossible to go through everything individually. So I can't go through the 45 beamlines and the 2,000 publications, of course. So I'll try to give you a little bit of flavor of what we're doing here a little bit later. So how do you access the ESRF? Well, there's in principle 3 different ways. You can either apply for the public beamlines. This is for the 32.5 that I mentioned before. Access is free of charge. The condition is that you publish the results, and this goes through the ESRF user office. You can also apply for beam time on the collaborating research group beamlines, the so-called CRG beamlines, in their own proposal systems. But for actually getting the beam for free, they have to give 1/3 of their beam time into our public program. So you can also apply to a beam time on these beamlines on this CRG that are operated by the CRG groups. And then there is the third stream here is proprietary research proposals, when companies come in and would like to do their own experiments that they are not forced to publish. And in this case, they have to pay, and this goes through our business development office. We have 2 proposal deadlines per year. The first one is in March, 1st of March. And actually today, we just started the selection. We have our so-called beam time allocation panels meeting today. And they have a second deadline on the 10th of September. So these are the two canonical ones. For some areas, like for instance, structural biology, you can apply for beam time throughout the year through what we call rolling applications, and they are continuously evaluated and assessed and beamline allocated if they are being accepted. So these are the types of proposals you can have at the ESRF. These are standard research proposals. This is an individual proposal where you ask for access to a single beamline for a single purpose, and these are valid for 6 months. You can also apply for long-term projects. These are proposals that are valid for 1 to 3 years, and they give you access to a whole series of beamline blocks. We have structural biology access, which is done in a very different way. These are the so-called block allocation groups. And the reason why we have this is because these experiments are usually very short. And we group many different research groups into these so-called block allocation groups. Otherwise, we would have several thousand more individual proposals to deal with, and this would be beyond our capacity. So all the structural biology is essentially organized in 50 to 60 access groups, these block allocation groups, which is the most efficient way of handling this. And as I mentioned, there's also rolling access proposals. Each proposal has a main proposer and some co-proposers, so you can collaborate with whoever you want to get access here. And the main proposer is, so to say, our unique contact point that we use for the entire subsequent process. And I'll show just a little bit of it. Once you have submitted your proposal, this proposal has to be evaluated first by the beamline scientist for feasibility. Then there is a scientific assessment by the beam time allocation panels, these 12 panels that I mentioned before. And of course, a safety assessment that is done by the ESRF safety group. All of this goes into the review committee meetings, which makes recommendations for the acceptance of these proposals. Then we approve the recommendations. It goes out to the beamlines. The beamlines accept the proposals and allocate the beam time to the proposals. So this is the traditional way of doing business here. These are the 12 panels. The panels actually review the proposals for a subset of beamlines. So each panel sees the proposals for all the proposals for a given beamline and can then make a fair and balanced allocation of beam time for the various scientific fields represented on those beamlines. So each committee has the full responsibility for the allocation on its beamline, and we have about 110 scientists who are doing this at the time, and especially today. So now let me come to the EBS project. Now, I told you that the ESRF was the first third-generation source. What does that mean? Well, if you look at any given technology, it generally develops in what's called the S-curve. So initially, you start with a new idea. You have technical obstacles to overcome. It takes some time. You have to get funding to get things rolling. And then once it's proven that it works, more investment comes, the development is much more rapid until with a given technology, you reach a point of saturation where even the injection of a lot more funds will not give you a lot more performance. So then if you would like to transcend the performance that you have reached at the mature level of this technology, you need the next development and the next one. Now, the ESRF was the third generation for synchrotron radiation technology, which started with the use of particle accelerators for particle physics. So it's not very applied, very, let's say, very fundamental science, physics essentially, where we were parasitic users. So these machines were not built and optimized for us. The second generation then were dedicated machines for the production of radiation, and already first insertion devices which were actually giving higher performance. The third generation then was fully dedicated machines with high performance insertion devices, so-called undulators. I'll show that in a moment. And now we think we have reached the fourth generation with what we call the MBA technology, or you can also call it complex band technology. We call it the HMBA, the hybrid multiple band achromat technology. So this is the new generation that is coming up. So what did that give us? So if you look what you see from the, in terms of source brightness, which is measured here in these units here, and spans many orders of magnitude, as you can see here on the left-hand side, goes from the first generation to the second generation to the third generation and then to the fourth generation, which brings us roughly here. And you can see this is an enormous improvement just in source performance. These are many orders of magnitude, which of course have to do with the fact that we improve the sources as we go along these different generations. The first generation, we're just using these bending magnet sources in those rings in a parasitic way. Second generation, dedicated sources with what we call wigglers, which actually force the electrons to undulate as they move along the path, but in a way that the individual rays emitted are adding up incoherently. And this means that for each pair of poles that you add, you actually get an amplification of the beam by the corresponding number of poles. Now, if you do the undulation in such a way that these intensities sum up, or let's say the amplitudes sum up coherently, then this actually goes with the square of the number of poles, which gives you a lot more intensity. And then if you do this fully coherent, like in the free electron lasers, it goes with the square of the number of electrons in there, which gives you another very big boost, which you can see here. But these are linear machines today. You can't do that in a circular machine and reuse the electrons many, many times. So now the third generation sources are typically sources that provide you a beam that looks like this. It's extremely asymmetric. It's very narrow in the vertical and very broad in the horizontal, which we call is the so-called emittance. So we have a large value for the horizontal emittance and a small one for the vertical one. And the fourth generation is now a set of sources that allows us to produce beams which are practically round. So you have the ratio of the horizontal versus the vertical size, which is closer to 1, which is giving you a much higher source performance, in particular source brilliance. In our case, this is a factor of roughly 40. And it also increases the coherence of the beam, which means you get coherent beams to do science that otherwise you can't do with incoherent beams. Now, these kind of sources, these third generation sources, serve the largest scientific community in the world. It's more than 50,000 users today, and it's still growing. Now, this is the classical setup for these sources. They were third generation sources. They were practically all built on this so-called double band achromat lattice, which was first developed in the US, and the ESRF was the first one for the third generation, where essentially you have 2 bending magnets per sector, and then you just add these sectors to get a closed path for the electrons. And if you add many cells, you have many of these radiation sources here, and normally we just put straight sections here at the end of it where we can add our insertion devices. Now, if you want to increase the brilliance, you have to decrease the emittance. So this is the source size that I showed you. And this one is proportional to the square of the energy of your electrons, to the third power of the bending angle, and a factor that is roughly 1 for most, is lattice dependent and is mostly in the range of 1, let's say. So you have 2 handles to actually make this emittance small or the brilliance high. You can either reduce the energy because you want to reduce the emittance, or you can reduce the bending angle. So you can reduce the bending angle by just making more cells with less bending per magnet. And this is what happened with the large storage rings that were built in the 90s, with the ESRF with 32 cells, the APS with 40, and Spring 8 with 48. And then you can add additional features which allow you to damp some of the momentum broadening that you get via the emission process in there. And this was done with the latest generation of sources in this third generation lattices, this DBA lattices. That was Petra 3 in Hamburg and the NSLS 2 in Brookhaven. So this is the endpoint for this DBA technology. Then there was an idea that already came up in the 90s, but couldn't be realized for technical constraints. The so-called multi-bend achromat lattice, where you actually decrease the bending angle by introducing a lot more magnets in there. And this is the first example of a ring that was built like that. This is the Max 4 ring. It's a 7 bending magnet lattice per sector. So these are the blue devices. You see 7 of them here, which is actually reducing the bending angle here with a third power. That means the emittance goes down and the brilliance goes up. There's only one problem with this design here, because this is an almost symmetric design, and this leaves you with a relatively small, what we call dynamical aperture. That's the envelope of all the stable orbits that you have for the electrons in the accelerator, meaning they are not so easy to operate. So for this reason, we came up with a new idea. This was this idea that I mentioned in 1992, where you actually marry the concept of a double band achromat with a multi-band achromat. The feature of the double band achromat is that you have here in the outer sections, you basically widen the optical functions of your electron beam in such a way that you can apply all the corrections that you have to apply to the electrons on their trajectory in this area here. And you have, where you have your insertion devices, you have actually a very small value for this optical functions, meaning you have a very high brilliance in these sectors, and that's exactly what you want. Now, if I go back and show you this one again here, you see the Max 4 lattice. You see that this is all relatively low, and this is leading to this relatively small or dynamical aperture, which actually makes the application of corrections, chromaticity corrections, and other corrections to the electron beam technically more challenging. So by basically marrying the basic principle of the DBA with the double band achromat, with a multi-band achromat, which keeps the optical functions very, very small in the center of the section and in the straight sections, but widens it here in the outer parts, you can actually build a storage ring that is as easy to operate as the old storage rings, but with a much higher performance. And this is basically what everyone is following today. So this is the lattice that we developed, which is improving the ESRF emittance by a factor of 40, roughly, but allows also to install a new generation of insertion devices, which will boost the brilliance even more than this factor of 40 that we gain with the emittance. So this is what this new lattice looks like. That's the old one here, the DBA, and this is the 7BA that we constructed for this lattice. And you can see there's a lot more magnets in there. It's a very tightly packed technical construction that is actually quite challenging to design and build, which nevertheless we managed to do. And you see here where the big gain comes from, because the emittance here scales like the inverse third power of the number of dipoles you have in here. And if you go from 2 to 7, that's roughly a factor of 50, right? Because it's the third power here. That's what's giving you the big gain. So this is essentially what we built, and we worked out the idea in 2013. We did the design in 15 and 16. 14 was for getting the approval. We built the machine from 2016 to 2019, meaning the manufacturing, the assembly, and the installation. and we started to operate it last year. So this is the commissioning schedule. I'm not running you through all of this, but just one thing to remember: this machine was so well designed that we actually managed to get full performance within 3 months. And this is a process that most other projects so far has taken up 3 years or more, because many of the newer machines haven't even reached their full performance yet, even after something like 5 years of operation. We got this after 3 months. And you can see this here. This is the beam as it looked like on the 17th of September last year, Thursday. This was just after we restarted our user operation. You see a perfect beam here with top-up injection, meaning almost no change in the electron beam current. It's constant at 200 milliamps. And with the emittance going down and down and down. And today we have already reached or surpassed the emittance values that were foreseen for this machine after just something like half a year of operation. So this is now at 120 in these units, 120 picometer radian. So the machine actually works exceedingly well. We have even better reliability than we had before, and it's now in full user operation. Now, I was asked also to talk a little bit about COVID. COVID changed our business model radically, because first of all, we had the difficulty of having to start up this machine under COVID conditions, meaning 80% of our staff being at home. We managed that, so we got everything working, the machine, the new machine, the source, and the beamlines at the same time. But when the users came back, or should have come back, we could not let them on site because of the COVID-19 restrictions, also with the travel restrictions, which means all the experiments have to be done remote with practically no users on site. More than 80% of the experiments today are done in remote, meaning remote control by the users. So this is how we actually went through that whole process. It was a very difficult process where we had to monitor very carefully how much staff we have on site to make sure that our staff and also the users later on, the ones that are here, are actually well protected. And as you may know, in France, we are now already in the 3rd confinement period that started at the 6th of April, and I hope that we will end this. But nevertheless, we have our 40 beamlines working, and we're doing experiments there. So this is how remote access looks like. This is a user from Australia here. This was very early on in, I think it was in September when these pictures were taken, where the user in Australia actually has access to all our control computers. These are actually several control computers on one screen where they can then control the experiments. And in this case, they did a coherent diffraction experiment on nanoparticles, which you can see here, and they could control everything from home, essentially. It's another experiment here. There was a group from Germany, from the University of Göttingen, which managed to acquire 16 terabyte of data with remote operation of a robot. And even the detectors were changed on this one. The group changed the detectors, samples, photon energy, so everything could be done remotely, which was quite a stretch for us to implement to make sure that the users actually have real access. So now, what do we do with all of this? Now, we have this machine. This is a high energy machine, so it gives us a lot more flux, brilliance, and coherence in the X-ray beams. And the two areas where we are particularly strong is the high energy end, because it's a high energy machine, and we have a lot of beam lines here in this area, which is essentially everything above 30 kilo electron volts. So we have a large number of beam lines here, and new ones that we're finishing next year, which are not even listed in this plot here. While in the middle region, this is around, let's say, somewhere between 2 and 20 or 30 kV. Coherence is the main new thing that we will exploit in the future very strongly. What we saw on the beam lines is we have a calculated performance, and we pretty much see on all the beam lines what we calculated. The increase in flux and flux density is what it should be. The increase in coherent fraction is what it should be, but we also see a significant improvement in beam stability, which is of course important when you work with ever smaller beams. You need to control their position ever more precise, which is actually what happened there. So this is the gain in brilliance, as you can see. So this is depending on the energy range you're working at and the source you have. It's somewhere in between 2 and 3 orders of magnitude. You find the same thing for the spectral quality when you look at this. These are undulator spectra. So these are the photons that you get on the different harmonics from the undulators as a and you can see this on the old storage ring, that's the red line, and the new storage ring, the blue line. You get much cleaner beams with much narrower harmonics and a lot more intensity in there. And that's precisely what we wanted there. You can also see that even the source itself is a lot more coherent, not just the photons. This is what you see here. This is an undulator spectrum of one of our, let's say, tender X-ray beamlines that works in between 2.5 and 12 keV. You see what the undulator spectrum here looks like. It's very coherent. You see a lot of interference fringes here, which tells you immediately that the source is really quite coherent. So we have not only a large increase in flux, but also a significant increase in beam quality in this machine. And you can see this here also on the high energy end. These are images of undulators where we change the gap between the magnetic poles, which is actually changing the radiation that is coming out of those magnetic arrangements. And what you can see here, for instance, at 100 keV, you see still a beam that is nicely interfering. That is something with our old machine would have just been a blob and not much else. So what do we use this for? I show you just a very, very few examples. We did already more than 1,000 experiments, but unfortunately, since they're not published, I can't show them here because the authors are very keen to keep the IP on this and publish this very nicely. So this is a beamline that just opened for the first time. And it's the first X-ray analog of a transmission electron microscope worldwide. So what you do in this case, you actually use a focus beam that you shine on a sample, and this sample is actually a bulk sample, so millimeter sized, and you put an objective lens in there, which allows you to get a full field image of your sample. If you take out the lens, you get a diffraction pattern, so you can get both, like in an electron microscope. You can either watch the diffraction pattern, or you can see a real space image, and these are real space images that you see here. This is a set of dislocations in the material. And this is what happens to strain fields that you see here in this little movie on the right-hand side. Is a time-resolved mapping of the change in the structure of a ferroelectric material upon reversal of the polarization. So you can directly see how the polarization here is reversed. Now, just to give you an example, these are very new experiments that were performed in 2020, and I have the permission to show this here, where you actually look at a highly deformed piece of metal, and we watch the recovery or recrystallization. And what you see here is in the diffraction pattern, this is when you take the lenses out, you see actually in the near field, you see all the scattering from the different grains in this piece of material. If you put the lenses in, you actually see what the individual grains look like. And the surprising thing here was that the parts that are the most deformed are actually growing. The expectation of the scientists was the exact opposite. The more you deform, the faster they disappear and are eaten up by less deformed parts. So this is actually the exact opposite of what you would expect. Now, this kind of microscopy now, where you can actually see the diffraction from the individual grains in a material all the way to a full field image at the same time, is something, and of course we can zoom in here, so we can change the magnification here, is something that is pretty unique. We will, however, never reach the resolution that they have in the electron microscopes, because they can reach angstrom or even sub-angstrom resolution, which we will never get. But we can do bulk materials, and we have much higher sensitivity by orders of magnitude to other properties of the materials, such as strain, for instance. So this is one example. Another example is where we use the superior coherence that we have in this new ring. And this here is for a bending magnet source here in the center of the ring, which is actually the very smallest source that we have at the ESRF now. There's a tiny little magnet here at the end of this green arrow here. And this one is producing extremely high X-rays up to 400 or 500 keV if you apply a very strong field, but at a superior level of coherence. And this is an ideal source for imaging. And you can see this here. This is a COVID-19 lung. This is something that is already submitted for publication. We've done lots of experiments on this, where we can actually study an entire lung and in the future, even a whole torso of a human down to cellular resolution with a full zoom-in function. So you can actually image either the entire object or zoom in into a particular cell if you want, right, continuously. This creates an enormous amount of data, and we've scanned lots of organs now already from COVID-19 victims, but also for other pathologies and healthy organs. And the amount of data you get from this is so large that there is only one way to analyze this, and this is using machine learning. Automated segmentation and analysis of the data, because this is essentially impossible to do by hand. And this is one of the future challenges we have. Another example here is this battery. And what you see here is actually a lithium ion battery. And we can do continuous zoom into this battery now, all the way from the device scale to the submicron scale. So this is all actually real data on a single experiment where you actually zoom in and get higher and higher resolution down to every individual grain in this structure here. The reason why we can see this is because we have the superior coherence now in these beams. This would have been impossible with the old beams that we had at the ESRF before. And you see this also in what I showed before, these nanoparticles that we can actually watch now individually, or we can go to much higher energy. And this is the first try at 41 kilo electron volts, because now in the future, for instance, if you take a fuel cell and you would like to watch the actual catalytic process in there that is producing the energy on particles that are really on the nanometer scale, we can actually zoom in onto an individual nanoparticle, reconstruct that nanoparticle in real life and watch how it is changing while it performs its function. Right? And this is something, of course, if you want to do this with a reactor, you have to shoot through the reactor, which means you need a very high energy. And in order to actually reconstruct what these nanometer-sized particles look like, you need a very coherent beam. And this is something we can only do with this source now here. Yeah? So these are just a few things that I wanted to show what you can do with this. And we know already that we can improve this easily with by several orders of magnitude. This was just the very first try when we got the new machine. And I cannot resist in showing you something at the very end, which is a very funny thing, because sometimes we get really fancy experiments here. This was actually a group with a very exotic application. They had integrated circuit, which is actually used in security applications, and they wanted to know from us if it would be possible to select one individual bit and rewrite that bit and basically uncode that chip. Right? So they went to one of our beamlines with a very small beam, and they actually found that bit, they rewrote that bit, and could actually reprogram this chip by just flipping one single bit in there, which in the end reset the whole column and changed the status of the entire circuit. So there's everything in there, from very fundamental applications or very applied applications, like I showed you with this COVID applications, up to something exotic like this one, where I actually use a nano beam to rewrite an integrated circuit. So there's a lot of things that we are still busy with. We're building a large number of new beamlines in the next 2 to 3 years. You see them listed here. We also have a far-looking accelerator program to even further improve the accelerators that we have. That's just a starting point, what we have today. And of course, since we are producing a lot more data than we did before, next year we will have the first beamline that can produce a petabyte of data per day. Now imagine if you're a user and we give you a petabyte of data, what you would do with that. my guess would be not much. So we have to help you with that. And that is, of course, something that we have to develop for the future and that we're actually working on. So with this, I'm finished. I hope this gave you a little bit of a flavor of what these facilities are good for, how they have developed over time, where we are today. And as I mentioned before, after just a little more than half a year of operation, we already have done more than 1,000 experimental sessions. And with, unfortunately, not many users on site, which we hope will change very soon. And we would like to have our users back. And with this, I'm finished, and I hope you enjoyed this presentation, and I thank you for your attention.
Thank you very much, Harald. I think all the audience can join us in clapping hands for you today. So it was a really interesting talk, and we received many questions. So first of all, I would like to ask if anyone in the audience feels like asking the question himself. Feel free to do it. Otherwise, we will start with some general questions. Okay, now they're writing so much. So, okay. First question for you, Harald. How are you working on the data analysis framework? How is this related to the HPC computing at Excel, for example? And is this a shared effort?
This is something that we're trying to develop throughout the entire community. For the time being, it is very difficult to access HPC centers, dedicated HPC centers, because they work on a different basis. On an HPC center, you typically have to write a proposal, and then you get access. And this could be, there could be a large time lag between the time you write a proposal and you do something. While at the ESRF, most of the time, we need immediate, at least online data visualization and reduction, so that you can actually see what you're doing during an experiment when you change parameters or conditions in an experiment. For instance, if you do a catalysis experiment and you have certain conditions and you change the conditions, in order to know how to change the conditions, you need to know what happened at the previous step, which means you need immediate data analysis. You can't write a proposal to an HPC center, right? This would only be for data analysis that is really well after the experiment. So what we need today is two things for the users. The first thing is, let's say, a relatively highly performing computing environment that allows you to do things online and in real time as you do the experiment. This needs to be here on site. And then a computing environment or access to a computing environment that allows you to do the post-experimental analysis, either at home or at some other center, if you cannot do it at home, because most universities do not have the resources that are needed for the massive amounts of data that we can create here. So this is indeed something that we're working on. We still don't know yet precisely where this will go. There's a lot of discussions going on. We are actually not working with the XFEL directly, simply because the XFEL is an independent entity and they're in a different country. So we have to first sort out our own local environment here. But we are talking with many different actors in this field in trying to find a real generalized approach on how this can be done. And this goes not only for IT hardware, access to IT hardware, but also to software. So that if you do an experiment at one source where you have a certain software package to do data analysis, that you can also use this elsewhere, which means you need a harmonization of the data formats, that they can actually read those data from different sources, different facilities. So there's a lot of things involved in this, and it will take many years to actually bring this to let's say full maturity. But we're making big steps now, because the source performance improvements in detector technology are so fast at the moment. This is in average an order of magnitude gain every 2 years. And this is something that it goes beyond the capabilities or capacities that most users have at their home institutions. You can't do this with a with a laptop anymore.
True.
We have another question. So very impressive talk. Could you say a bit more about remote users versus on-site users and the carbon footprint of travels? Because I imagine a downside for the ESRF staff is that they have much more placed on their shoulders with remote users. So is that in fact the case, Harald?
Yes, this is indeed a real problem for us because the way we normally operate is that we have 10,000 users roughly coming on site, and they're usually the top experts in their field. They know their samples, they know their sample environments, we don't. So even if they send us their equipment, it takes us probably 3 times as long to make it work.
Yeah.
And sometimes it will maybe not work very well because we don't know exactly how to clean things, how to prepare things, how to set them up.
Precisely.
So, which means this will reduce throughput, and the risk that experiments fail will be very big. And sometimes the really complicated experiments, like in catalysis or so, we can't even do them anymore. So
yeah,
you could.
It's something to take in account, but yeah, it seems like you're still putting lots of efforts in allowing users to perform remote experiments. If it's
we do that,
for the user.
But it's not sustainable. If we would have to run, I mean, people swallow this for the time being. Our employees swallow this. They do near impossible hours sometimes to make experiments happen. But this is not a long-term operation model for sure. So either we need a lot more people or we need a much higher degree of automation, which in the first place needs people to develop it and implement it.
Yes.
So the best example is structural biology, which is essentially fully automized today, but it took 20 years to develop. A large amount of money, many people in 20 years. This is not something you do easily overnight. And structural biology has the advantage that they all work with one standardized or 1 or 2 standardized sample holders that can be easily the handling can be easily automized, and you can use robots for that. Now imagine you do catalysis on 100 different catalysts for very different applications, for liquids, gases, and solids. So a single sample environment won't do the job. You need lots of them, different ones, right? And somebody has to develop that if you want to run this completely remotely. So we think for a facility like us, where people come to do complicated experiments, they don't come here just to run capillaries on a powder diffraction beamline. Most of
course, yeah.
So for this, my firm opinion is we will still need users to come to a large degree. If you want to do this kind of high-end experiments, this will be necessary. Yes.
Yeah. So, of course, I think we should really acknowledge all the ESRF team for the great efforts they put it in this very unusual time. We continue with another question, a little bit more general. Very enlightening talk, a broad and controversial question. In terms of cost performance right now, which technology is more convenient for generation synchrotrons or felts?
Well, I mean, this answer is easy. There's a factor of 10 to 100 in between the cost for an individual experiment at synchrotrons and at X-FELs. So it's factor 10 to 100 more expensive to do a X-FEL experiment than a synchrotron experiment. You see this just with the sheer number of experiments we do.
Yeah.
Okay, and then there is like a general question about the postdoc program that you mentioned before. Is it usually bounded to a beamline or to a certain research project, or how can a PhD student increase the chances to get a postdoc position at the ESRF?
Actually, we have close to 70 postdoc positions fixed, financed in the ESRF budget. Each beamline has, per definition, 2 postdoc positions, and they are for 3 years. So we have, in a rolling way, there's always postdoc positions becoming available at the ESRF. So if you check our recruitment pages, there's always postdoc positions open on some beamlines. Or just if you're interested in a particular beamline or technique, just contact the scientists and ask them. They can tell you when the next position will become available, they're more than happy to talk to you.
Yeah, that's a great tip. So we will probably ask another question, and then we're running out of time.
So there's this question. First of all, thanks a lot for the very interesting talk. With the very high brightness, a huge number of photons is delivered into a pixel, voxel. Thus, a significant amount of energy is introduced. How do you address the potential of changing the sample while measuring? The higher the brightness, the more awareness of radiation damage is there. Is it right?
Yes, this is true. And for many experiments, that simply means you do your measurements faster, or you find conditions such that you do not damage the samples. Just one possibility, for instance, is that you actually translate the beam so that it doesn't stay too long on one position. But that, of course, means that your sample has to be homogeneous. Because if it's heterogeneous and you look at a different position, then of course you get different results. One way to do this, for instance, is if you use liquid jets, which allow you also to do, let's say, time-resolved experiments very nicely, because you could, for instance, have what we call microfluidic chips, where you bring two different reactants together in the chip. And depending on the distance where they start to react, this is basically the timeline. You can do time-resolved experiments on fresh material all the time. So you don't actually, even if you have damage, you have fresh material all the time. So what we do normally in most experiments, we figure out what the best conditions are. In some cases, when you work with solids or, for instance, with biological material, that means that we go to cryo temperatures, because the samples survive a lot longer in cryo conditions, if you can do that. But it's true, this is definitely something we have to deal with all the time. And let's say a significant part of the beam time sometimes is spent in finding the right conditions so that you actually see the effects you want to see and not something else you don't want to see.
Yeah,